Hello and welcome to this 1.3 video for calculus. This video is going to talk about limits and finding limits analytically. So we've already talked about finding limits graphically, we've talked about finding them numerically. In class we went over some of the properties of limits, some of the basic properties. But in this video we're going to talk about how to find some limits that don't have a basic property to them. They're a little bit more in depth, and how we can analyze them with our brains and figure them out that way. So, the first thing we're going to talk about is functions that agree at all but one point. And we'll start with this limit. Limit as x approaches 9 for x squared minus 4x minus 45 over x minus 9. So the one thing that you'll notice is that direct substitution is not going to be an option for this particular limit. If we put in 9 in for this limit, what's going to happen is we're going to get 0 on the bottom, which already throws a red flag right there. But you'll also notice that if you put 9 in up top, that you're going to get 9, or you're going to get 0 on the top as well. Okay? So we cannot put 0 in because it gives us 0 on the top and 0 on the bottom. So we're going to have to think of a different way to do this. Now obviously you could do it numerically, plugging in values close to 9. You could do it graphically, check out the graph, see what it's approaching. But let's see how we can do it analytically. This function is very interesting in the way that it's set up because of its factors. If you factor this function, it factors into x minus 9, x plus 5 on the top. And this is interesting because the top and the bottom have similar factors. And because they have similar factors, that's actually the reason why we get 0 on the top and the bottom if we plug 9 in. Now the interesting thing about these two factors is that no matter what you put into them, no matter what value of x you plug in for these two factors, they're going to be the same thing. Alright, if you plug in 10, it's going to be 1 up here and 1 down there. If you plug in 20, it'll be 11, 11. If you put in 9.01, it'll be 0.01 and 0.01. So really, no matter what, these things always cancel each other out, because when you divide them out, you're going to get 1. There's one particular spot where they will not cancel out, and that spot is 0. Alright, so if you think 9 into this function here, you put 9 into the bottom as well, that gives you 0 over 0. And that gives us something that's undefined. Okay, so 9 is not going to work. But everywhere else, those two factors cancel out to 1. And the nice thing about the limit is that we don't care what happens at 9. If you remember, we care what happens as we get close to 9. So it is not wrong to write the limit like this. And essentially what we did is we divided those out to 1. Now normally we could not divide those out to 1 because at 9 it gives you an undefined point. But remember, with the limit we don't care what happens at 9. So that's the reason why we can divide those out. Now this particular limit we can evaluate by just direct substitution. Plugging in 9 gives you 14 for an answer. And so this particular limit turns out to be 14. We figured that out without doing it numerically, without doing it graphically. We analyzed the function. Okay, and that's what we're talking about when we're talking about analytically. And this whole point up here that says functions that agree at all but one point, this function here that we started with and this function here are exactly the same function except at the point 9. At 9, this function is 14, and at 9, this function is undefined. Other than that, these two functions are exactly the same because this factor, x minus 9 over x minus 9, always divides to 1 except at 9. All right, so that's one way to analytically find the limit of a function. Let's do another one. All right, so looking at this particular function, I know I can't directly substitute in 3. It'll give me 0 on the bottom, which is either an asymptote or a whole. But when I find out, putting in 3 on the top also gives me 0. So what that tells me is there's a common factor on the top and the bottom of x minus 3. All right, 3 makes both a 0. Unfortunately, I don't know how to factor this readily. All right, I could factor it, but I don't know how to factor it readily. So if I want to factor it, one thing that I can do is use long division. Actually, I'll use synthetic division because I think it's easier. Use synthetic division to divide out the factor of x minus 3. Okay, and so there I factored out x minus 3. So my new limit could look like this. All right, so really all this process was figuring out, well, I know that x minus 3 must be a factor of the top here because I'm getting 0 when I put in 3. So if I use synthetic division to factor out that x minus 3 factor, I'm left with x squared minus 6x plus 9. And hopefully you remember a little bit of that from pre-calculus. But the reason this is helpful is because now, again, we don't care what happens at 3 because it's a limit. We can, in a sense, cancel those out and find the limit as x approaches 3 of x squared minus 6x plus 9. And again, this is something we can do by direct substitution. Plug in 3, I get 9 minus 6, I'm sorry, 9 minus 18 plus 9. I actually get 0 doing that anyway. Okay, so this function approaches 0. Now notice in both the problems I did, not once did I ever get rid of the limit out front until I was able to directly substitute by plugging in 9. All right, if you don't have this limit out front, you can't do this step where you cross out the x minus 9s. All right, so you need to continue to write this limit always until you plug in, directly substitute in that 9. If by chance you accidentally forget to write a limit, you lose points. If you just feel like leaving the limit off, you lose points. All right, I'm very serious about this. You need to continue to write this limit until you directly substitute in 3. All right, at this very last step, I could now put in 3. So I put in 3 and I can just write my answer. At this very last step on this one, I could now put in 9. So I put in 9, I don't have to write the limit anymore. All right, but if you don't lose that limit, if you do lose that limit, it's no longer correct. Okay, so that's our first way to find limits analytically, and we did it for functions that agree at all but one point. Stay tuned for the next couple videos, and we'll talk about how to do it for other types of functions. Have a great night.